Today we are going to talk about the future of perception using AI agents. The perception of the world is made up of different data modalities like vision, hearing, taste, and smell. A future where AI agents can look, read, and process data in different modalities like image, text, sound, or even memes is absolutely game-changing. Let's understand why learning concepts that's present in an image and connecting it with the meaning found in the text is so important for an AI model to understand. In the paper, Experience Grounds Language, the author proposed a notion of a world scope to track the progress in AI development. They define 5 world scopes to track the progress in AI. The first level of the world scope includes AI agents which were trained on the Corpus Dataset. These datasets became the basis on which AI agents were able to learn the meaning in words by projecting these words into a vector embedding space and solve tasks like finding synonyms or antonyms of target words. Corpus datasets are restricted to a single data source, and therefore that limits the grammar and the domain that's covered by the text. They typically range in the size of 100,000 to 1 million sentences. AI models like Word2Vec and Glove have been successful in creating a vector embedding space of words that captures the semantic information between them. Both are trained on corpus datasets. After AI models had been trained on the corpus datasets, the corpora in NLP grew to include large web crawls. This added the use of unstructured, structured, multi-domain, and multilingual data into the training datasets. This absolutely increased the size of these datasets and brought them to the scale of the internet. The second scope includes AI models that are trained on internet scale datasets. They are constantly growing with web scraping bots adding information to them. Neural network models like BeRT and T5 have been successfully trained on these internet scale datasets to do tasks like sentence completion or language translation. In our mind, the world around us links all modalities, whether it be vision, sound, temperature, everything together. And our mind tends to create a single world model that helps us to navigate. Therefore, it is a sign of progress if AI agents are able to do the same. The third level of the world scope are the perception datasets. These datasets include data of different modalities like images, text, sound files, and structured data. Through web crawlers, these datasets are also constantly increasing in size. The multi-modal image and caption dataset Coyo right now is at 700 million image and caption samples. The neural network-based model, CLIP, which was given in the paper Learning Transferable Visual Models using Natural Language Supervision, and the neural network model Flamingo, given in the paper A Vision Language Model for Few-Shot Learning, have been shown to be successful in training on 400 million plus caption and image pairs. And since these two papers have been authored, one can find many AI models on Hugging Face which are able to embed images, sound, video, 3D models in the same single multimodal embedding space. As we all know, neural networks excel at creating these vector embedding spaces from training data. And these vectors can be used to solve a variety of different target tasks, as long as we curate the right set of loss functions and train the neural network architecture on enough data. We will make use of this property of a neural network architecture by training it on a perception dataset, use the right architecture and loss function, and thus create a single multimodal embedding space for images and text. Let's start that journey by looking at the history. Word2Vec and Glove were able to predict the next word in the sequence or synonyms or antonyms for any target word. With BeRT, it became possible for neural network architectures to process longer context. This meant BeRT was able to successfully do tasks such as document or email completion and language translation, and even question answering. Clip and Flamingo are able to show that image and text can be projected into the same single multimodal embedding space, and then these vectors can be used to successfully do tasks like text-to-image retrieval, automated image captioning, and even multimodal question answering. Let's get a bit deeper into Clip. Clip uses a two-tower architecture. Here, the image and the text are embedded by a visual encoder and a text encoder, respectively. All we need to do is train the architecture which is responsible for embedding the image on concepts that are present from the text data to create that single multimodal space. And similarly, we need to train part of the architecture that embeds the text using concepts from the images during the backpropagation step. The paper presents the idea of a contrastive training function that is able to jointly train the visual encoder and the text encoder on a single multimodal training task. The Clip model was first trained on 400 million images and caption. In comparison, the visual encoder that's part of the Clip architecture is generally pre-trained on the ImageNet dataset, which has 1.2 million images. The Clip architecture has 5 key parts. The first is the preprocessor. The preprocessor transforms the caption or any input text into a sequence of tokens. This tokenization happens through byte pair encoding. Once the input text has been tokenized, it is run through the second part of the text encoder, which transforms that sequence of tokens into a text embedding vector. The third and final part of the text encoder is the projection model. The projection model transforms the text embedding vector to a multimodal embedding vector for the target task. The fourth part of the Clip architecture is the visual encoder. Just like the text encoder, the first part of the visual encoder takes as input an image and converts that into a visual embedding vector. After that, the visual embedding vector is run through an instance of the projection model to project the image into the same single multimodal embedding space in which the text encoder projects the text. The fifth and final part of the Clip architecture is the contrastive training function. As we have discussed, that function is used to jointly train the visual encoder and the text encoder on a multimodal task such as text-to-image retrieval or text-to-image generation. Now that we have a fair idea about the Clip model, let's talk about some applications of this single multimodal embedding space which contains both images and text using the clip model. First is zero-shot classification. Using a training data set for any supervised image classification problem, we can take the class label and using some smart prompt engineering, convert that into a caption. And now we can run the clip image encoder on the test state on any image in the test data set and predict which class and its corresponding prompt engineered caption the image is most closely related to. The second application is text-to-image retrieval. Now, using the text encoder, we can embed any search query into the multimodal vector space and then use that embedding to find any similar images in your test dataset. Let's talk about the limitations of clip. Clip is poor on fine-grained classification such as differentiating models of cars, flowers, or systemic tasks such as number of objects in an image or digits. Clip is really poor on novel tasks that are unlikely to be used in pre-training, such as classifying distance to the closest car in an image. Clip generalizes poorly to out-of-distribution images, such as handwritten images. Clip cannot generate caption. It can only find alignment between text and image. Now, in the final part of this video, we are going to go through a Colab notebook and train a clip model using the story narratives dataset. Let's go. You need to connect this Google Colab notebook to a local Jupyter runtime. For this experiment, I have connected it to a Jupyter server running on my home rig, which has two 3090 GPUs. You can always just subscribe to Google Colab Pro to run GPUs on the cloud. So to start off with, we need to set up the Python environment running on the Jupyter server. It involves installing a bunch of libraries and then importing them. We will be using the localized narratives dataset to train our clip model. This is a unique dataset that's available open source, and it includes a dataset of images and captions, where the captions are quite detailed. The next set of cells are going to download the localized narratives dataset along with its images and annotations. We'll skip through this because I've already run those cells once. In the next cell, we are going to take the input images and the captions and store it in TF record files. This allows us to shard the training dataset across multiple files and use the advantages of parallelization during training batches. Now, in the next set of cells, we are going to implement the clip model. As we have talked about earlier in the video, it's made of 5 key parts. The first is the projection head. The projection head is the part of the architecture which takes as input an image or text embedding and projects it into the multi-modal embedding space of a fixed embedding size. This projection head is used in both the visual encoder and the text encoder. The projection head is just a set of stacked, dense layers, and after the first layer, every other layer has a residual connection, a dropout ratio, and a layer normalization to regularize it during multiple batches of training. The second key part of the clip model is the visual encoder. The visual encoder takes as input an image, converts that into an image embedding, then runs it through a projection head to calculate the multi-modal space embedding vector for that image. In this experiment, we are going to use the exception network as the pre-trained backbone for the image encoder. It's available on the keras.applications Python library. The third key part of the clip model is the preprocessor. The preprocessor takes as input the caption and converts it into a sequence of tokens. These tokens are calculated using byte pair encoding. So in the text encoder, we run the caption through this preprocessor, get a sequence of tokens, run that through a pre-trained backbone of a text embedding model and get the text embedding, and then run that text embedding through a projection head to get the Multi Modal Embedding Space vector for that caption. In our experiment, we'll be using the pre-trained BeRT as the backbone for the text encoder, and similarly, we are using the BeRT preprocessor for it. The fifth and final part of the clip model is the contrastive training. As we know, the clip model is a two-tower architecture with a visual encoder and a text encoder. We need to figure out a way to backpropagate concepts from the caption into the visual encoder, and similarly backpropagate concepts from the images through the text encoder. In order to do that, we'll be using a technique given in the paper, learning transferable visual models from natural language supervision. As given in the paper, we'll be using the categorical cross-entropy loss function to calculate the loss terms. These loss terms increase in value if the cosine similarity between an image and its corresponding caption is low, and the loss value decreases if the cosine similarity between the embedding vector of an image and an embedding vector of any caption in the training batch is more or less the same if we replaced the image with its corresponding caption. Using this loss function, we are able to backpropagate the same concept present in the image or in the text through both the encoders, and thus create a multi-modal embedding space. As you can see here, I have loaded the two encoders separately in two different GPUs to reduce my training time by parallelizing the backpropagation through the two-tower architecture. We need to set the embedding size of the multimodal embedding space, and this number really depends on the amount of VRAM that you have available on your training GPUs. In this run, I have 48 gigabytes of VRAM available on my training GPUs. So with that amount of memory, I could go up to 92 as the embedding size. In this training experiment, I'm using 200,000 image and caption pairs to train the model, and I'm going to train it for 5 epochs with a batch size of 96. Now that the training run has started, we just need to wait. Well, finally the training run is completed. Here I trained the model only for 5 epochs, but I would recommend you go for 10 to find the best model weights for your training dataset. You could also go for a larger batch size. I chose 96, which gave me 2074 iterations per epoch. Let's take a look at the loss curve from our training run. Looks like we didn't overfit the training dataset except in the 5th epoch. Now let's move forward and see how does the multimodal embedding space help us in doing image retrieval using natural language queries. Once we have the embedding vectors for each of our training images, in the next step, we'll take as input the user's query, run it through the text encoder to get the embedding vector, and find the image which has the highest cosine similarity in the multimodal embedding space with the input query. In order to find the top images relevant to the input query, I'm calculating the exact cosine similarity between each of those vectors. If you're dealing with a larger set of images, you might want to look into vector DBs or vector indices such as Annoy from Sonos or Fast from Facebook or Meta to speed up this process. Now let's try a few different input queries and see how useful is the embedding space in helping us retrieve the most relevant images for our text. Let's start off with something simple like many people rhyming. In the final part of this notebook, we'll do a quantitative evaluation of the clip model for the image retrieval task. We will use the top K accuracy metric to quantify the accuracy of the clip model. In this metric, a true prediction is counted if for a given caption, its associated image shows up in the top K highest similar images found in the embedding space. Remember, when we do the ranking, we are only loading a fixed batch size of images to compare and contrast. In a vector DB, you will not be limited by the number of images you could load and compare against. But since here we are working in a Jupyter environment, the top K images are retrieved from a total of 96 images that create the embedding space. So our validation accuracy came out to be 78.51%. What that means is for the 20,000 validation images that we ran through our visual encoder, for every batch of 96 images, whenever we picked a caption and looked at the top K highest matching images, the corresponding image of the caption showed up in 78.5% of the cases. There are several ways to improve upon this accuracy metric. One is you could go for higher embedding size, as we discussed, increase the training batch size, or go for a larger training data set. I hope you now understand and feel capable to train a clip model to give the power of perception to your AI agent and let it navigate multimodal data when dealing with text and images. If there are other AI architectures which you have found to give the perception capability to your AI agents, please comment below. Thanks for your time.